Hello, welcome to Module 26 of the course on application of spectroscopic methods in molecular structure determination. We will continue with the infrared spectroscopy. In this module, we will look at examples of OH, NH and CH stretching frequencies in the particular region in the infrared spectrum. For the purpose of illustration, several spectra were taken from these two books, that is Organic Chemistry's Organic Spectroscopy by William Kemp and Spectroscopy by Pavia and others, and I am grateful to these two sources. For the illustration purposes, the spectra have been taken from these two books. Now, the functional group that could be easily or unambiguously assigned from an infrared spectrum are typically alcohols and phenols, amines, nitriles, carbonyl compounds, aromatic compounds and nitro compounds. Although the infrared spectra give a wealth of information about a lot of other functional group, from the organic chemist point of view, these are the functional group that one normally looks for in the infrared spectrum. The presence or absence of these functional groups can be unambiguously assigned. Now, the OH, NH, CH stretching region is a very unique region. This is in the left hand side of the infrared spectrum, starting from 3600 inverse centimeter to 2400 inverse centimeter. It's a fairly broad region, but within this region one can classify the CH, OH and NH frequencies based on the masses of the atoms that are attached to it, namely carbon, oxygen and nitrogen as the case. In the infrared spectrum, the CH region is typically from 3300, the base value is about 3000, but it extends from 3300 to some 2800 or so, and the OH region is typically between 3650 to 2400 or so, with the base value corresponding to about 3400 inverse centimeter. The NH region corresponds to 3500 to 3100. Typically the base value is essentially same as the OH base value. Now let us have a look at the CH region. Almost all the organic compounds will have a CH functional group, because particularly unless it is a completely fluorinated or completely halogenated substance, they will have the CH group present in there. Therefore, the CH region is fairly rich in information but highly complex in nature in terms of analysis. It may be difficult to interpret this region due to overlapping bands that appear in this region. In other words, since the OH, CH and NH appear in nearly the same region, interpretation of the region can be somewhat difficult for the CH region. And let us have a look at the various types of CH groups that one can have in the organic molecule. This is something we have already seen. Depending upon the bond strength, the stretching frequency keeps increasing with the increasing bond strength. In other words, an acetylenic CH, vinylic CH and an alkanic CH is compared here. The alkanic CH is around 2900 inverse centimeter, whereas the alkenic CH is about 3100 inverse centimeter, and an acetylenic CH is 3300 inverse centimeter in terms of the stretching frequency of the CH bond. This CH bond in the acetylenic unit is the strongest bond, therefore it comes at the highest stretching frequency value. As you can see here from the strength of the bond, this has the strongest bond, and this is the next strongest bond, and this is the weakest bond among the three, which is also reflected in terms of the bond length of the CH bond that is indicated here. These are examples of spectral region corresponding to the CH region. The entire infrared spectrum is not shown, only the region from 4000 to 2000 is shown, because that essentially covers the CH region. In this region, if you look at carefully, if it is an alkane, this is a linear alkane, this is a decane molecule. The CH region essentially contains only sp3CH, so that comes as a bunch of peaks in the region, narrow region of about 2800 or 2900 inverse centimeter. In other words, it is coming from 2800 to some 3100 inverse centimeter as multiple peaks that are seen corresponding to the CH stretching of the sp3 CH hydrogen, so sp3 carbon hydrogen stretching is what is seen in this region. Now, when you take an alkene, this is actually octene, 1 octene as an example shown here. This has both the sp2CH as well as sp3CH. One can clearly see the sp2CH to come at a higher frequency or higher energy region compared to the rest of the CH, which nearly looks as this one here. So this corresponds to the sp3 hybridized CH stretching frequency, and this sharp singlet kind of a thing that is seen here at a higher frequency region correspond to the sp2 CH stretching frequency. Now when you go to a terminal acetylene, the terminal acetylene in this particular case is 1 octane is taken as the example. The terminal acetylene CH comes at an even higher frequency. The olefinic CH comes around 3150 or so, whereas the terminal acetylene peak comes around 3200 or so in this particular case. So among the CH, sp3 CH comes as the lowest, sp2 at a higher, and sp even higher in terms of the frequency where it is being observed. If you are taking an internal alkyne which does not possess the CH, terminal CH, acetylenic CH, this particular band is missing here, essentially because this is an internal acetylene. Internal acetylenes do not have acetylene hydrogen, therefore that particular band is very clearly missing in the case of 4 octane compared to the spectrum of 1 octane, which has the CH corresponding to the sp-CH stretch of the CH functional group. Now let us go to alcohols and phenols. We are talking about the OH stretching frequency. OH stretching frequency is a very characteristic feature in an infrared spectrum. It is very strong and broad in case of the OH, which is hydrogen bonded in nature. It is centered between 3400 to 3300. Due to hydrogen bonding, it is generally very broad in nature and also a very intense signal. Now dilute solutions you can see the free OH in dilute solution. The stretching band corresponding to the free OH comes at a higher frequency value compared to 3400. This is 3600, and generally it is very sharp, and usually a weak band is what is seen for a free OH, because most of the hydroxy containing compounds exist as hydrogen bonded system. So in order to see the free OH, one has to considerably dilute the solution. That is one of the reasons why this band is fairly weak in dilute solution. In addition to the OH stretching frequency, one should also see the CO stretching frequency, which appears in 1260 to 1000 inverse centimeter. This is a characteristic region for the CO single bond stretching frequency. So the OH bending also comes in the region of 1440 to 1220, but it is often obscured by the band due to the CH3 bending, hence it is not a reliable thing. So the reliable information that one can get for an alcohol or phenol kind of a molecule is a stretching frequency, whether it is a hydrogen bonded OH stretching frequency or a free OH stretching frequency, depends on the dilution of the sample, and the CO stretching frequency, which appears around 1260 to 1000 inverse centimeter. Here is the spectrum of this particular alcohol, which is hexane 1-ol, for example. This is a neat sample. In other words, the liquid thin film is taken between two sodium chloride plate in the form of a very thin film, and the infrared spectrum is measured. One can see a very broad band in the region between 31,000 to 3100 to 3300 or so, 3400 or so, with the maximum around 30 to 50 or so in this particular region, and this corresponds to the OH stretching frequency. Then you have the CH stretching frequency, which is coming at a lower frequency values, which are around 2800 inverse centimeter. Then the CO stretching is a very characteristic region around this is 1100, so this should be around 1050 or so is the region where the CO stretching, single bond O stretching frequency comes. So this is a characteristic spectrum of an alcohol kind of a sample. In the case of phenol also, you will have the sp2 CH band. You can see the difference gap between these two bands are fairly high, because this is around 2800. When it is moving to an sp2 closer to a 3000 region, it is closer to the OH peak, for example. The OH broad peak that is seen here is essentially because of the hydrogen bonded OH stretching frequency of the phenolic compound here. In addition to the CO stretch which comes here, because of the C double bond C being present in this phenolic molecule, one can also see the C double bond C stretching. So essentially, this region, which is devoid of the C double bond C stretching frequency, tells you that this is probably an aliphatic kind of an alcohol, whereas this is probably either a olefin containing alcohol or an aromatic unit containing alcohol, because of the fact you have a C double bond C as well as the C single bond O stretching frequency appearing in this region, which are characteristic features of an aromatic phenolic kind of a compound. Now, in order to see the free OH stretching frequency, one need to really look at the spectrum in a very dilute solution. Typically, carbon tetrachloride is used as a solvent. 3 different spectra of the same sample is given here. It is an alcohol sample. This is a neat liquid is what is used for this sampling. Here a dilute solution is used, and here a very dilute solution is used. Dilute and very dilute is only a relative term in this particular case. one can very clearly see in the neat spectrum a broad band because of the OH stretching frequency corresponding to the hydrogen bonded OH stretching frequency is what is seen here. Plus you can also see the CH stretching frequencies in this particular region. When you have a dilute sample, there are two bands which are appearing. One is a sharp band at a higher frequency, and then your usual broad band like what you saw here around 3300 as a maximum. Same frequency around 3300 is the maximum that you see here. Maximum intensity in terms of the transmittance, for example, and this is essentially because of the free OH, and this is essentially because of the hydrogen bonded OH. When you have a mixture of free OH as well as the hydrogen bonded OH, this is a characteristic feature by which you can identify the free OH and the hydrogen bonded OH. When it is further diluted to a very dilute solution, the hydrogen bondings are broken, and you don't have much of the hydrogen bonded system here. Now you have only a free OH. The weakness of the intensity of this particular band is essentially because it is a very dilute solution. As you can see here, even the CH band has become weaker in terms of the intensity because of the dilution nature of this particular sample that is being investigated. There is also a OH stretching frequency in carboxylic acid that appear in the same region as the phenolic and the hydroxy functional group. Only difference is this is much broader because carboxylic acids are typically hydrogen bonded in nature, both in solid as well as in dispersions. But only thing is that in the case of a phenol or alcohol, there will not be a C double bond O stretching frequency, whereas in the case of a carboxylic acid, in addition to the OH stretching frequency, one should also observe a carbonyl stretching frequency in the carbonyl region. Now this is the example of isobutyric acid sample. One can see a very broad envelope of OH which is even masking the CH peaks also along with it. So it is a fairly broad peak is what is seen for the OH, consisting of this entire envelope of stretching frequencies, which also masks the CH stretching frequency, which you can barely see as a spike on the broad band of the OH stretching frequency. Carbonyl stretching frequency is also there. That is why it is a carboxylic acid derivative. This is a spectrum of benzoic acid. This is actually in the dispersion in a Nugent mull, whereas this is neatly taken as a neat sample. In other words, liquid sample is taken neat and the solid sample is dispersed in Nugent mull. The peak corresponding to the Nugent mull are identified by a dot. You see the dot here, which is corresponding to the CH stretching frequency of the Nugent, and this is a C double bond C stretching frequency of the Nugent, and this is also because of the Nugent, for example. So the OH stretching frequency essentially is the broad stretching frequency that you see in this region corresponding to the carboxylic acid OH, and the carbonyl, conjugated carbonyl, that what it is coming around 1700 or so in the case of the benzoic acid, as a carbonyl stretching frequency as well as the OH stretching frequency corresponding to the carboxylic acid. In the case of amines and anilines, NH stretching frequency occurs at slightly higher frequency compared to the OH stretching frequency. Primary amines will have two bands. This is a very characteristic feature of primary amines because of the symmetric and the asymmetric nature of the NH stretching frequency. Secondary amines, on the other hand, will have only one band corresponding to NH stretching frequency. Tertiary amines do not have NH stretching frequency because there is no NH bond in the tertiary amines. In addition to the NH stretching frequency, one should also observe the CN stretching frequency at 1350 to 1000 inverse centimeter in the case of amines. Now this is an example of butylamine, normal butylamine. It's a primary amine. In the primary amine, this is measured as a neat liquid, for example, and one can see in the NH region a doublet kind of a thing. This is the pattern that one need to look for when we are looking for a primary amine kind of a system, and this is a CH region and this is a NH region, very distinctly delineated in this particular case. In addition to that, the CN stretching frequency also appears in this case. For example, around 1050 or 1150 or so is the CN stretching frequency which is appearing in this case. Now let us go to dibutylamine. This is a secondary amine. This is a primary amine, so you see a doublet corresponding to the asymmetric stretching and the symmetric stretching of the NH. In the case of the dibutylamine, which is a secondary amine, there is only one band that is seen for the NH stretching frequency. This is the CH region and this is the NH region. The CN stretching is appearing as a fairly intense band. You can see the intensity has increased here for the CN. The intensity for the NH has decreased, which is the other way around in the case of the primary amine in the case. So one can compare the NH region of the primary, secondary and tertiary amine. Tertiary amines do not have any NH, so you don't see any peak in this region. With the blue dotted region, for example, does not have contain any peak because there is no NH in it. This is a tri-N-butylamine, which is a tertiary amine. This is di-N-butylamine and this is butylamine. So one can see very clearly in the case of butylamine a doublet, in the case of di-N-butylamine a singlet, and there is nothing in the case of the tri-N-butylamine, as the case may be, as in this particular case. This is a distinction between two isomers. You have 2-methyl-aniline, which is a primary amine, and N-methyl-aniline, which is a secondary amine. Essentially, from the NH stretching frequency, one should be able to tell the difference between a primary amine and a secondary amine. In the case of the primary amine, it appears as a nice doublet in the infrared region of NH stretching frequency region, whereas in the case of the secondary amine, a sharp singlet is what is observed for the NH stretching frequency. Here you have the asymmetric stretching and the symmetric stretching of the NH, whereas here is only one type of NH, so one type of NH stretching frequency is what is being observed. In both cases, of course, one observes the CN stretching frequency. This corresponds to the CN stretching frequency, which is also present in the case of the secondary amine as a CN stretching frequency, which corresponds to this particular value here. In case of amides also, one has NH stretching frequencies, but it is always accompanied by C double bond O stretch as well as the CN stretch. The amide functional group has the NH stretching, CO stretching as well as the CN stretching. In the case of amine, this band will be missing. The carbonyl band will be missing in the case of amines and anilines, but amides do have carbonyl, so there will be additional bands because of the carbonyl stretching frequency in the amide. Primary amides as usual show two bands, symmetric and asymmetric stretching of the NH stretching frequency. Secondary amides show only one NH. Tertiary amides are devoid of NH stretching frequency because they do not have any NH present in this system. So you can see here, this is a butyramide, the primary amide. So one can see the doublet kind of a structure here for the NH. This is a Newjoule peak, and these dotted peaks are the Newjoule peaks, for example. This is measured as a Newjoule mole. This is a solid sample. Whereas in the case of N-methyl acetamide, this is a neat sample as a liquid. So there is only a single band that is seen for the NH stretching frequency. In both cases, in addition to the NH stretching frequency, one can also see the carbonyl stretching frequency corresponding to the amide carbonyl of this system, which is coming at a value around 1650 or 1670 or so in these two cases. This is benzamide. Benzamide again has two stretching frequencies. This is a primary amide, so NH asymmetric stretching and NH symmetric stretching is what is seen in this particular case. In addition to that, the carbonyl peaks are also seen in the case of the benzamide as an additional peak in this. This is measured as a KBr pellet because benzamide is a solid. One can measure the KBr spectrum. So what we have seen is a very important region where you can distinguish between CH, OH and NH stretching frequencies of various functional groups in which they occur, and we will continue in the next module with the carbonyl stretching frequencies. Thank you very much for your attention.